Okay, so another problem from top to finish. Linear non-homogeneous. So, like I said before, the first step is dealing with the homogeneous part. So we're gonna do x prime equals 1, 4, 1, 1 x bar. And obviously we start with the characteristic equation. The trace is 2, so lambda squared minus the 2 lambda, 1 minus 4 is the determinant. And this factors nicely into lambda minus 3, lambda plus 1 equals 0. Okay, so the first eigenvalue, lambda 1 equals 3, we are in the first case, right? So distinct real eigenvalues. Subtract 3 from the main diagonal. 1 minus 3 is minus 2, 4, 1, 1 minus 3 is minus 2, and find the eigenvector. Look at the rows, they are dependent, that's reassuring. That's what should happen, the rows are dependent when you find the eigenvector. I can pick the second equation, v1 minus 2, v2 equals 0. And the easiest choice I can think of for the eigenvector is to plug in 1 for v2. And then v1 equal v2. So that's the first pair of eigenvalues, eigenvectors. Continue with the second eigenvalue, lambda 2 equals minus 1. By the way, pause or try to do this ahead of time, ahead of me, just to check for practice. When we subtract minus 1, that's 1 minus negative 1, so that's 2 and 4. And then 1 and 2. 1 minus negative 1 is 2. Once again, the rows are dependent. That's expected. Okay, so second equation, I'm going to pick it again. v1 plus 2, v2 equals 0. And then v2 would be, I'll choose again 1 for the second entry. And that gives me minus 2 for the first entry. So second vector is minus 2, 1. So we're done with the homogeneous part. Let's write down the solution. C1 2, 1 e to the 3t plus C2 minus 2, 1 e to the minus t. So that's the homogeneous part. Let's look at the particular solution. So now we start looking at the non-homogeneous term. And remember what I told you before, it's clear that we need a linear term to match the second component. When I say linear term, I mean a quantity like this, at plus b. Now notice this also takes care of a constant. So you don't need a separate constant to match this. But you do need another linear term for the first component of xp. Remember, when you choose xp, both components of each component of xp matches both components of f bar of t. So that means I need a linear term for xp on the top position here on the first component, and I need another linear term for the second component. Well, I can't assume beforehand that the first entry of xp will require just a constant. I cannot assume that beforehand. I need to make it as general as needed. Yeah, I mean in that sense, in the sense that it should match both entries of f bar of t. So that's the correct choice of xp. And now we can proceed with work, right? We're gonna plug in at plus b on the left side, and we're gonna take the derivative. On the second step. And combine everything into a single column on the right hand side. All right, so what is the derivative on the left side? That's AC. And matrix multiplication, 1 times quantity AT plus B plus 4 times quantity CT plus D, and then plus 0, right? When you combine it with the column representing the non-homogeneous part. And again, 1 times AT plus B plus 1 times CT plus D plus the second component of F bar of T, which is 3T. So how do we match the equations? Well, in each entry, when we match them, we match the coefficients of T and the constants. Coefficient of T, there's no T on the left. That means it's 0. And that should match A plus 4C. The constant is A. And that should match B plus 4D. Plus 0, right? But I'm not going to write that down again. No T on the left. We look at second component now, second entry. 0 on the left for T. Pay attention here, the coefficient of T on the right side comes from 3 entries, 3 terms, A plus C plus 3. And finally, the coefficient, the constant, which is C on the left, should match B plus D. And this is the system that gives you these 4 coefficients. Again, don't jump quickly to write down matrices to solve the system. If you look carefully, you should start with the first and the third equation, because that's just a system in A and C. So we have to take advantage of that, because usually it's faster to solve. So I'm going to take this equation and then combined with this equation, the third one. A plus C equals minus 3. So move the 3 over. A plus C is minus 3. I can quickly subtract the 2 to eliminate A. So 4C minus C, that's 3C. 0 minus negative 3 is 3. And so that C equals 1. That means C equals 1. If C equals 1, for example, from this equation, I can quickly find A. Minus 3 minus 1, minus 4. Now, since I know A and C, I can group now the second and the fourth equation, and that gives me another 2 by 2 system in B and D. So B plus 4D is A, which is minus 4. I found it here. B plus D equals C, which is 1. Once again, I can quickly eliminate B by subtracting the 2. So 4D minus D is 3D. Minus 4 minus 1, that's minus 5. So D equals minus 5 over 3. Now, don't assume that you won't have any fraction. Fraction may still happen. That's not the end of the world. So D equals minus 5 over 3. And let's see, if I plug it in here in the second equation over here, that's B minus 5 over 3 equals 1. Move it over. And so B equals 8 over 3. All right, so we finally found the particular solution to be, now make sure you write these coefficients in the right order, right? So AT, A is minus 4, so minus 4T plus B, which is 8 over 3. CT, that's going to be just 1 times T, plus D, which is minus 5 over 3. So notice it happened that all of these coefficients were non-zero, in fact. Not only you couldn't have assumed that this doesn't contain T, as it turns out, all of these coefficients are non-zero, which again justifies why you need to take XP in its most general format possible. And again, for completion, remember the general solution is the sum of the two, the sum of the homogeneous part and the particular solution that we just found. And maybe I should have thrown in an initial condition here, but let's not make this problem longer than it is already. So just remember that if you have an initial condition, you deal with it at the end of this process, like with all initial value problems. Deal with that at the end to find these coefficients C1 and C2. So that's it for non-homogeneous linear systems. Next lecture will be our last in the course. Not the last video. I might add later on, I don't know exactly when, maybe other addendums basically to some of these concepts. But in this class, we're going to have one more lecture, and namely, how do we use linear systems to approximate non-linear ones, which is actually the starting point of lots of interesting stuff actually in differential equations, because in modeling work, most of the systems are non-linear. So it begs the question, why do we deal with linear systems for so long? Why do we care about solving them completely when real life is made of non-linear models? So there's a very good reason, and namely, in many situations, not all of them, but in many situations, one can approximate locally a non-linear system via linear ones. So that's one justification why linear systems are still very important. So I'll see you next time.